Hello everyone and welcome to the Calculus Grade 12 classes. And in today's class we are going to finish our Unit 4, which is dedicated to curve sketching. And today in particular we're going to discuss the concavity and points of inflection on the graph. So in previous units, in Unit 3 particularly, you discovered useful properties of third derivative in problem solving involving velocity, acceleration. Is it right?
Yeah.
So now, today we're going to study another nice property of second derivative that will be really handy for us in curve sketching. Before we start, I would like to refresh your memory about derivative and what is the second derivative. Are you comfortable to answer that question, Yusuf? Or would you prefer me to explain you that?
What's the question?
So second, let's say if we have a initial function, what information first derivative gives us, how it describes the graph basically, and what information second derivative would gives us in such case.
Uh, well, the first derivative of a function provides like the slope at a particular point.
Yeah, so or first derivative you can also say it's rate of change, right?
Yeah,
Because it's basically speed of a function, how fast point goes along this curve towards that point, right?
yeah, it gives us the instantaneous rate of change of uh of the function at a given point, which can help
Yeah,
us like understand the behavior of the function as it changes with respect to the input.
yeah,
Like an
absolutely
expression.
right.
Yeah,
So second derivative in this case would be derivative of the first derivative, right?
yeah. So
When we
this
differentiate one more time. So we're now differentiating different curve, which is plotted based on the first derivative function. Remember, because derivative is in fact function that can be plotted.
Yeah, so like the second derivative provides us like insight on how the rate of change of the function is changing. Like
Absolutely right.
yeah,
Absolutely right. There is no better explanation of these because if you remember what is second derivative in terms of distance, velocity, and acceleration,
yeah,
second derivative in this case, in this chain of three factors would be acceleration. And if you think about it, at the same time, you can have first derivative positive.
yeah.
Are
Let's
you sure it's
say this,
acceleration?
pardon?
Are you sure it's acceleration?
Sorry, I cannot
The
understand.
second derivative, isn't it velocity?
No, for second derivative is just a name.
Yeah,
In case where we are looking into function of displacement,
yeah.
first derivative of function of displacement would be velocity,
Oh,
and
okay, yeah,
second derivative of function of displacement would
yeah,
be acceleration,
yeah,
because acceleration is a first derivative of velocity.
yeah. I got it.
So I would like you to take a look at this example. To the left-hand side, you can see that my derivative, first derivative, would be positive, right? Because my function is growing.
Mm-hmm.
As well as on this side of the curve, my function is constantly growing, and it's easy for you to see now, right?
Yeah.
So, but if you take a look at the second derivative of this function, you would discover that it takes negatives value at some points. And I'm gonna tell you that these values are to the left from this inflection point. This point is called inflection because to the left and right hand side, uh, we have different sign of second derivative, which gives us this kind of, bend shape here. And it happens because, as you see here, even though we have positive velocity, if you prefer, or positive first derivative, but you can see that the slope of this line is decreasing, right? Our line becoming more and more horizontal over time. Am I right?
Yeah.
So it means that we are slowing down our speed, right? We are not growing as fast as we began at this point, for example. At this point, we had first derivative looking up here. When we move along the curve, it changes the direction closer to the horizontal position. And inflection point is a point such like this one, because first of all, to change, first of all, we're gonna see that the sign of the second derivative changes. And one more thing to notice, that basically to the left hand side, we are slowing down approaching this point, and second derivative thus would be less than 0. And here you can see that we start with really not relatively slow speed, right? But we keep growing, our velocity increasing. So it means that our acceleration is positive, right? Because we are accelerating ourselves. We are not decelerating ourselves. Make sense?
Yeah.
So I'm gonna clear this drawing. We don't need it anymore. And let's move on. Talking about outcomes, basically what you're gonna study today is define application of second derivatives in terms of curve sketching, how it could be useful for us so in order to plot a given function. I would like you to participate with me in this investigation real quick. So let's go A, B, C, D, E, F, G, all one by one. It's not hard at all. So let's sketch the graph of function f of x equals x squared. So let's say it's going to be here. You can also plot it if you wish, but I believe this derivative is going to look like this. Because it's standard derivative, you see we don't have any constant which would give us vertical displacement. Plus we have a positive coefficient in front of the variable. So it's looking upward and has vertex at 0.00. Am I right?
Yeah.
So determine first derivative of this function. Use first derivative to calculate the slope of a tangent to a curve at the points with the following x coordinates. And sketch each of these tangents. Oh, let's simplify this task a little bit. Let's just find the first derivative. Alan, what would it be?
2x.
Perfect. Equals 2x, right? So now let's evaluate it for given values of x. Let's take two values to the negative, one neutral, and two to the positive, right? So for example, -4 would gives us
-8.
yep, -8. Then we can also have -6. And to the other side, we're gonna have 0, then 6 and 8. Identical points, right? Symmetry over y-axis. Is it correct? So number C, are these tangents above or below the graph of y equals f of x? So let's say
What if
I
it
have,
means?
let's imagine I know approximately how it should look like. Like I can, let's imagine I'm a robot that can draw a tangent line perfectly, okay? So I have point -8. I have point -6. Oh, no, 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 no. -4 for x, -3, 0, 3, and 4. And here we have negative, here we have positive value of a function. And in these points, I'm gonna have a tangent line, right? These are points I investigated.
Mhm.
Let's imagine I'm a perfect robot and I can plot this tangent line. Oh, I actually can. Oh. Like this. This tangent line would look like this. This would go even higher up, yeah. Does this make sense to you guys?
Mhm.
Yeah,
So what I want to take a look at here is that you see when we elongate our tangent line, it doesn't cross the curve, does it?
No.
And the reasoning for that, because our function growing up faster and faster. You see this?
Yeah.
First derivative gives us a greater slope in each consequent point.
Mhm.
And because of that, tangents in these points are going to be below the curve. Does it make sense?
yeah,
Okay. Yeah.
But on the other hand, if I would have function like this,
That's
my tangent would be above the curve.
well. Okay. Yeah.
Make sense?
Yeah.
Here it also doesn't touch as it, but it's above the curve.
Yeah.
And if derivative is above the curve, most likely it means that we are losing speed, right? We're decreasing because we're like tilting over this function on top.
Okay.
So describe the change in the slopes as x increases. I basically already told about it, right? That slopes is increasing as x going farther from x, both directions.
Mhm.
Determine second derivative. How does the value of f second derivative of x related to the way in which the curve opens? How does the value of this derivative relate to the way first derivative changes as x increases? So let's see what would be the second derivative.
2.
Absolutely right. So second derivative is 2. And what does it mean, guys? What do you think about it?
Um.
How does the value of second derivative impacts the change as x increases?
How does the value of the way x increases? Hmm. Um. I mean it doubles each time. Is that true? No. It accelerates 2 times its speed.
So basically what you can see here that we have positive second derivative.
Mhm.
It asks you how the value of second derivative related to the change of first derivative. And here we can clearly see that the value of second derivative is always positive because we don't have any variable here, and no matter what value x takes, our second derivative would be always positive.
Mhm.
Is correct? And this is what basically we get in this example. And basically what I can see here, if my second derivative is positive, it means that my function growing to the both sides. Isn't it? So if my second derivative is positive, my initial function, yeah, so here we ask how first derivative changes. So if second derivative is positive, then first derivative is increasing as it getting away from the vertex. Is it clear?
Yeah.
Mhm.
So if we would repeat all the same parts for minus x square function, we would have a vertex that looking down, parabola looking down. And we're gonna have a slightly different values. But if you plot the first derivative, you're gonna see that to the left-hand side, we're growing,
Yeah.
but we are growing, but second derivative slowing us down, right? Because you see, we're reaching this vertex, and it means we are slowing down. It's like, remember, jump. It's like trajectory of thrown object horizontally to the ground at an angle. Do you recall that from physics?
Yeah.
So this is exactly because when you throw something up, we have gravity that pulls us down, which gives us negative acceleration, basically. And that's what makes this top point of a flight be possible, right? That's the reason why we're not just flying into the space. And so in physical example, second derivative, which has a negative sign, is a sorry, not the second derivative, but a factor that decelerates us is the gravity. In this case, it's just a formula. And in this formula, we're also going to see that the second derivative going to have -2, right? Second
Yeah.
derivative would be -2. It means that our function is always affected by the acceleration in a negative way. As you can see it here, basically we're dropping down drastically, but we're slowly trying to climb up, right? And after this vertex in the middle, we're starting to climb up. That's what positive second derivative gives us. It means that we are always growing. Make sense?
Yeah.
And negative second derivative would gives us that we're always decelerating, or we're slowing down. And that's exactly what we see here. We start with enormous speed, almost vertical, right? Then the tangent line inclines farther and farther to the horizontal position. And eventually it's 0, right? We don't have any speed. And then we begin to go backwards. You see?
Yeah.
We moved this way, now this way along the line. So, Yusuf, can you formulate how second derivative affects the first derivative?
Um, how second derivative affects a first derivative?
Not affects, but let's say this what information about first derivative, second derivatives gives us, right? Because second derivative is based on a function. Here we discovered that, for example, in two vertex, if second derivative is positive, it means that we are always accelerating, right? Growing tangent, slope of a tangent line tends to climb up. Make sense?
Yeah,
The same, the opposite stuff happens when the derivative is negative. So the velocity is constantly decreasing for us. Unless, if we have continuous movement, it's going to decrease up to the point where we stopped and started moving backwards. So in general, can you generalize it?
so like the second derivative of the function provides information about like the concavity of the graph's like function of the function of integer graph, and like the inflection points and like the rate of change. Uh, I'm not sure exactly like how to explain it.
Yeah, basically you can say you were right, and you can also add that a sine of second derivative
Yeah,
affects rate of change of initial function, right?
yeah,
If second derivative is positive, it means that rate of change increasing. If second derivative is negative, it means that rate of change decreasing. Make sense?
yeah.
Any questions so far?
No,
So did you plotted this function for you?
no, 1 second.
Don't worry, we're gonna have more to practice today.
Okay, yeah,
So let's not waste time. And here's second investigation, and we're gonna do the same stuff with function x to the third power.
Mhm.
So first we're asked to determine at which points first derivative equals 0. So first derivative would be 3x squared, and this equals 0 when x equals 0.
Mhm.
Only point. Determine intervals on the domain of the function. Determine intervals on the domain of the function such that second derivative less than 0, equals 0, and greater than 0. So now let's find second derivative, and it would be 6x, right? And I'm gonna have 3 intervals. First interval would be from negative infinity to 0, not included.
Um,
And here I'm gonna have basically interval equals to a single point. We're gonna have single point in middle. This is when second derivative equals 0, right?
yeah,
And we're gonna have one more interval to this side. And let's here I draw a line in order to examine the sign of the of the second derivative, right? So first interval, I can see that I'm gonna have negative values in this interval, and here I have positive coefficient. So as well as we did with the first derivative, remember exactly the same approach. Now we evaluate the sign of second derivative. And second derivative in this case is going to be negative. In 0, it equals 0, right?
yeah.
In positive, it is positive. Okay, okay. This is what we were looking for in C. D, for values of x such that second derivative less than 0, how does the shape of the curve compare with your conclusion in investigation 1? Alan?
mm, the shape of the curve,
Yeah.
well, it's not symmetrical. It comes up from the negative side, in the middle, and then increases. So it's always increasing.
So this function is always increasing, you say?
Yeah.
Yeah, and we can see it from the first derivative because our first derivative is always positive.
Hmm.
But here we're asked to examine a second derivative, and second derivative is not exactly whether function growing or not, right?
Oh,
Second derivative is about if we're growing faster and faster with every moment, or we're growing slower and slower with every moment. That's what second derivative is about. Make
it's
sense?
Yeah,
faster, faster.
Pardon?
You're going faster and faster.
Why would you say so?
So if it's from coming up from negative, you're gonna always grow faster because sorry, I'm eating right now. You're gonna go up faster because well, if you plug in -4, you're gonna get -24, and then so on. The number is gonna decrease, which means you're approaching 0 at a faster rate each time it's not constant. Because if you plug in 3, you're gonna get 18.
Unfortunately, you're confusing it with first derivative again, yes, Alan. Because
What?
first derivative tells you the rate of change, how fast are you going. And second derivative tells you whether you're increasing your speed or decreasing your speed. I understand already that I'm always going forward, right? In this case, because my first derivative is always positive.
Mhm.
But if I look at the second derivative, I can see that on this interval, my speed is going to be taken from me. Acceleration is negative for me here, right? Isn't it clear? So it means I'm going to go slower and slower. Make sense?
yeah,
Okay.
After reaching the point of inflection 0, you're going to see it's going to be a point of inflection.
Yep.
My basically my second derivative now goes along with my first derivative. So, and they help each other. First derivative increases, and so my speed is growing up every single time, right? And my second derivative also shows me that I have positive sign here. Thus, I'm going to increase my speed. If you take a look at these values, I don't know why you said that you're going to have always greater and greater speed, because if you substitute it into the first derivative here, you're going to see that to the left and right hand side from the from 0, you have positive value. But as you approach 0 from the left hand side, you're going to see that value of first derivative getting smaller and smaller. Tell me what's going to happen to this function if x equals -1/2?
Well, it's still increasing. It's just not as big.
Why is it increasing? I don't get it. You mean the value of a function increasing? Why increasing?
Yeah.
Yes, but I'm not questioning whether it's increasing or not. I'm just saying that the way it's increasing is getting slower.
Yeah.
This is gonna be your function. And you can
Mhm.
see here that my tangent line to a curve goes not steeper and steeper,
Mhm.
but rather it's getting more horizontal. You see this?
Mhm.
My
Yeah.
speed is decreasing. And on the opposite side here, I'm growing up. As easy as that.
Okay.
So here you can see that you have point of inflection. You have a side where your second derivative makes you slow down. Here your second derivative makes you accelerate. And overall, this function constantly growing, right?
Mhm.
If you see, we're also gonna have, is this gonna be a critical point, guys?
Um. Yeah.
Yeah, basically, this is gonna be a critical point, even though this is not local minima, local extrema, but this is point of inflection, and point of inflection is also a critical point. You can understand critical points as a references for yourself when plotting those graphs, okay? If you can find value of those critical points, their position, define how function behaves around those critical points, you don't need to find the value of a function at each and single point in order to plot it. Make sense?
Yeah.
So here, let's summarize what we know so far. So from these investigations, we can make a summary of the behavior of the graph, concavity, and the second derivative. So the graph of y equals f of x is concave up on an interval a less or equal than x, which is less or equal than b, in which the slopes of f of x are increasing. On this interval, second derivative of f of x exists, and second derivative of f of x greater than 0. The graph of the function is above the tangent at every point on the interval. Make sense?
Yeah.
Any questions, guys?
Give me a second. Can you explain that one more time?
So concave up basically means that we have basically intentions to increase our velocity,
Okay.
if you prefer. It means we have positive acceleration. You see, second derivative greater than 0. Concave up gonna be also characterized by tangent line being lower than the slope. Can you see this?
Yeah.
Yeah.
So what is concave up, basically? It means that on interval, slope of the tangent line is increasing.
Okay.
And if the slope of the tangent line is decreasing, it's concave down.
Okay. So it's just the direction of the it's just how the tangent line, if it increases or decreases.
Yeah, or how the tangent line not increase or decrease, but how the slope of a
The
tangent
slope. Yeah.
line increasing or decreasing.
So this one here, that one is concave up, and this one's concave.
Both
No,
of them concave up.
they're both concave up.
Yes, because if you take a look at the slope of a tangent line, you can see that the angle is increasing for each one of them.
But don't you read it from left to right?
Pardon?
Don't you read it from left to right, the graph?
Here, it's also increasing because slope of a tangent line is negative here. And it's getting less negative. It's becoming less negative over time, so it's increasing.
Okay.
And here we have slope of a tangent line positive, and it's becoming more positive.
Okay.
Oh, okay. Yeah.
Makes sense?
Yeah.
Here, you remember when we're going down along the curve, so our first derivative is negative, right? We have slope of a tangent line negative. Remember that, yeah?
Yeah.
Because slope of a tangent line equals first derivative. If our first derivative is negative, means the slope of a tangent line is negative. Okay, can we move on?
I'm just writing it down on my book. So a simple way of putting it is that if the slope of the tangent is increasing at a faster rate, it's concave up, as
No,
well.
not faster rate, but if slow. So you can say a second derivative greater than 0 implies implies that slope of a tangent line is growing, or for example, f prime of a is less than f prime of b for this graph, right?
Yeah.
And here, same stuff. Does it make sense? In both cases, we have same 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 relation between the first derivative in beginning and at the end of the interval. Because keep in mind, right now we're looking on an interval, on certain interval. That's how we're describing what is concave up. Because if we just talk in general case on endless scale, how we can bring it up to some area that we're going to investigate. That's why we bring in to interval. Is it clear that first derivative in f of a is greater than, or is less than first derivative in f of b?
Yeah.
Alan,
Yeah, but it's kind of confusing, but yeah.
what is confusing?
Oh, it's because normally for the first graph that you'd read it from left to right, so you'd
And
see.
you're reading both of them from left to right.
Yeah, it's just like I would look at it and say it's decreasing because the slope is decreasing.
Yes, that's right. And you're not wrong.
But
Value of function is decreasing.
yeah,
The instantaneous rate of change is increasing. The slope of a tangent line to a curve is going to increase.
oh, the instantaneous rate is increasing.
Yes, because here on this part of this graph, you're going down faster than you're
Yeah,
going down here.
yeah,
Does it make sense?
yeah,
If
Yeah.
you so it means if you're going slower in negative direction that you used to before, it means you're accelerating. Make sense?
yeah. That makes more sense now.
And you're not wrong because you're confusing first derivative and second derivative. And notice that I'm not these two thing are not conflicting with each other. Your function can decrease, so your first derivative is negative, but at the same time, your second derivative can be positive.
Okay.
And the same stuff to the opposite direction. What if my graph would look like this? What if my graph looks like this? Here,
But
you still can say, you're still gonna say that my I'm growing, right?
yeah,
But why I'm growing like this and not straight up like predicted? Why like this? Alan?
there was an inflection,
No.
was it not?
Because second derivative would change its sign to negative and it would start to slow me
Oh, okay.
down.
Okay.
Make sense?
And that would be concave down.
Yes, because here you can see that the tangent line is above the curve.
Okay. Yeah, I get that now.
So can we move on?
Yeah.
Concave down, please go ahead. Enjoy it. I give it a minute and ask me any question if it still needs to be clarified.
Okay.
Please read it through. I want to give you another example of negative second derivative, so it's more intuitively understandable to you. Imagine I'm driving in the car. I'm gonna plot it. I'm gonna plot the graph here. Imagine I'm driving in the car. I'm accelerating. I'm increasing my speed. I'm going forward, right? But I'm slamming the brakes now. I slammed the brakes somewhere here. What happened to me? You see, uh, even oh no, my curve would look like this. I was accelerating, right? Going faster and faster over a period of time. My delta t is getting less, but I'm covering more distance over the same period of time. My delta s is growing, right? Here, for example, same period delta t, change of time. I'm covering less distance. Less, yeah, right, guys? Do you agree with me?
Yeah.
So my velocity is thus smaller here, but it's greater here. Positive acceleration. Makes sense? Positive second derivative thus. And another thing, tangent line is below the curve. So positive second derivative, right?
Hmm.
But I'm slamming the brakes. And I'm decelerating almost instantly and I'm slowing down. This is a horizontal line would mean I stopped. I'm not changing my ass anymore. And what happened here? When I slam the brakes, brakes are basically equivalent to negative acceleration. Brakes are taking velocity from me. Make sense?
Yeah, that makes more sense now.
Perfect. So do you have any questions about concave down?
So
No.
concave down, the slope would be above the graph all the time.
You mix it up a little bit. Not the slope, but the tangent line.
Tangent line, sorry.
Tangent line would be above the graph.
Okay.
And also, first derivative at A would be less than in B, right? So
What was that again?
first derivative in point A should be less than first derivative in point B.
Okay.
Make sense?
Yeah.
Slope of a tangent line is getting more negative,
Okay.
guys.
Yeah, I got it.
What about this curve? Same. Slope of tangent line becoming more negative, more horizontal.
Which
When before inflection point and after inflection point, it becoming more steep and it eventually wants to be vertical. Make sense?
mhm.
Any questions about this?
No, I'm
No.
good.
Yeah.
Perfect. So another cool property of second derivative, as we saw an example where we plotted the parabola x squared, right? We saw that our second derivative is always positive because it was just constant, positive constant number, right?
Yeah.
If you see that your second derivative, so if your second derivative in this local minimum or this what it's called. So let's say you find this critical point C, x equals C, right? And if your second derivative greater than 0 in this point, it doesn't equal 0, right? Because if it equals 0, we have inflection most of the time. And when derivative equals some positive value in this point, it means that our initial function would try to grow to both directions from this point. Or it's going to decrease from the left to this point and increase from this point into the right. But take a notice how they plotted this here. They made two arrows, right? Two arrows looking both directions. So they want to emphasize that you can see this shape that your second derivative test can give you is based on the sign of the second derivative. Is it clear? Not on the value of the second derivative, but on the sign. So if your second derivative is positive in this vertex, so it means that the function would grow into both directions from this point. But I understand, Alan, why you're confused now, because before we read from left to right, but you can say it would grow in both directions because we just would like to know shape of the graph, right?
Yeah,
We're not particularly describing how it would act to the left and right. We just say starting from this point in both direction, we're going to grow. Like if we start from this point, of course. Or we can say another thing that if we have like polynomial function of second power, like x squared plus x minus 1, right? If we have something like this and second derivative is positive, it means it's going to be parabola looking upwards. So basically, I would like you to memorize this step. Please try to relate this inflection points and all the other stuff to critical points, right? Remember, in first investigation, first thing we did, we found sorry, we found the first derivative. It was somewhere here. Oh yeah, here. See, they ask us to find when the first derivative equals 0. Remember? And this is already critical point, right? If x equals 0, if the first derivative equals 0, isn't it?
yeah,
It's gonna be a it's gonna be basically local extrema or local maxima, local minima. So let's move on here. You have any questions about second derivative test? It's pretty much basically the same as first derivative, but now we interpretate our information differently. If before we were looking into local minima, local maxima, vertical, horizontal asymptotes with first derivative, with second derivative, we're basically more interested in the shape of a curve. Now you should see how it works all together, because you have critical points from first derivative test, right?
yeah,
And you have basically attitude of the curve between these critical points or aside from them based on second derivative test. Does make sense? And now to plot the curve, you need to find points, right? Let's say you need to find points and how your function behaves in between those points. And second derivative, that's exactly what gives us whether I'm going to go like this, or am I going like this? Or am I going like this from one to another point, or am I going like this? Make sense?
yeah,
Look, I'm gonna The first one is I have a negative second derivative. You see why? Because my tangent line is outside of a curve. And here I would have negative second derivative as well, right?
Yep.
But look here, I can plot it as positive second derivative, right?
Yeah.
Mm, But how?
Why? How? It's just imaginative case.
Oh, okay.
I'm explaining that how you connect first derivative test and second derivative test.
Okay.
Imagine that this point you
Oh, okay.
found from first derivative test, right?
Yeah.
And whether it's going like this or like that, you found from second.
Because of the sign of the function.
Yes, sign of the second derivative.
Okay, so if we went with the red would be a positive, the black would be a negative sign.
Yes, yes.
Okay.
And remember why? Because it's either concave up or concave down. And concave up and concave down defined by the sign of the second derivative on the interval. Because sign of the second derivative should be same on the whole interval to say whether it's concave up and concave down. Because if I have something like this, and yeah, something like this, like we had before, right?
Yeah.
And I take interval from here to here, I can see that the sign of my second derivative is not constant along this whole curve. Here it would be negative, and here it would be positive, right?
Yeah.
So that's why we need critical points. We would like to slice the graph into areas, into intervals. And once we do that, look, we found critical point in the middle here in 0, 0, right?
Yeah.
And now we have two intervals. On one of them, function has negative second derivative, and on the other one, function has positive second derivative, and we can easily implement our techniques to plot this graph.
Okay. I got it.
So no questions, guys?
No, not any right now.
So let's clarify it. Second derivative positive means it's local minimum of a function.
Yeah.
But sorry, and not exactly like that. So we can say that the graph would be concave up, and we're gonna have a local minimum in a point, in certain point, if second derivative is positive in this point. Because if you have second derivative equals 0, for example, in this point, it doesn't mean necessarily that graph is going to concave up, and it doesn't necessarily that this is going to be local minima. And you're going to see it in our further example. Here, about local maximum, you can see that in this case, second derivative is negative. Make sense?
Yeah.
Yeah.
So, but if the second derivative equals zero, the nature of the critical points cannot be determined without further work. And this is the most interesting part of it. A point of inflection, you see? If derivative in the point equals 0, if second derivative equals 0, that and it's really important that our second derivative should change sign after crossing this inflection point. Make sense?
Yeah,
Exactly what we see here. We already discovered this prior in this class with you guys, right?
yeah, we discussed that before.
So let's move on. Statement number 5. All points of inflection on the graph of y equals f of x must occur either where second derivative equals 0 or second derivative is undefined. Again, points of inflection, critical points with first derivative equals 0 or undefined, and now second derivative equals 0 or undefined. Does it make sense?
Yeah,
So this is what you want to use for your second derivative test. And just remember that you're always looking for you're always looking to simplify the question, right? To simplify the task. And that's basically how people came up with this first and second derivative test. Because if you have really complex function, you would like to evaluate it only once and be able to plot it, right? You don't want to make dozens of calculations. And that's how they did it. They say, what if it's equals 0? Or what if it's not defined at all? You basically simplifying your own task by applying restrictions or applying properties. And you check whether your prediction right or not, because you say, I would like to find values when my x square equals negative value, but x square never equals negative value, right? So you cannot substitute x square to negative value.
yeah,
As
so
well as some function would never take 0 values, and you try to implement the first or second derivative test to it, you're gonna see that, for example, you don't have this point that it equals 0. So this is just a number. I would like you to see this as number of techniques and tools that you can implement. I want you to see a equation further in your courses, and you'll be like, oh, okay, let's see what happens if it equals to 0, right? You shouldn't know right away what is the right approach. You just need to try it. And ways of trying it, try and error, is to try whether it's 0 or whether it's undefined. Make sense?
yeah,
So let's do this one example and call it a day. So using the first and second derivative test to analyze the cubic function. Who would like to do it, guys?
I could try.
It's not hard. I would hope that you don't look here. Let's just think about it together before you look into the solution, okay, guys?
Okay.
I understand it's hard not to look there, but let's practice control, right?
yeah,
So let's think about it. Using first and second derivative test. First thing that comes to my mind is find the first derivative
Yeah.
and find the second derivative.
So the first derivative would be 3x squared.
Yeah, we have it right here.
Oh, okay.
Yeah, sure. Now you can look. We made a statement that we would like to find the first derivative. If it's already there, let's take a look at it. So first
And
derivative would be like that.
you'd want to
So
find critical points, I think.
yeah, first let's perform the first derivative test first, as we did in previous classes. It should be pretty easy. So what is the set of actions when you're performing the first derivative test?
Factor. And then
Sorry. Yeah, in this case, you're right. We factorize, but first, I would like you to say that we are looking for points when derivative equals 0.
0. So set it equal to 0.
Yeah, and factorizing is a technique, right?
Mhm.
Do you know the difference between tactics and strategy?
Kind of.
So our strategy in this case for first derivative test is to find when derivative equals 0. This is a strategy of first derivative test. And tactic that we can use to do that is factorization of polynomial functions. It's a tactic that we use because you can use same tactic for different strategies.
Mhm.
So go ahead, please.
Factor out of 3. And then you would get 3 times x squared subtract 2x subtract 3. And then you would do that. You would try to find the product sum. You would get a moment to write it down so you can see it or no.
Sorry, I don't really understand why you're looking for product sum here. To find solutions for this quadratic function,
Yeah.
right?
Yeah.
Mm-hmm.
So you would
Product sum. Okay, product sum.
you got
You
right
can
there.
write it. You can write it.
Product and sum, those are equal. Product is equal to -3. Sum is 1.
Isn't
Oh no, sorry. You're right. You're right. Sum is
so?
-2.
Yes.
And then you would get 2 numbers that multiply, so it would be maybe 3 and -1.
If sum is -2, I believe it should be -3 and 1.
Okay.
All right?
Yeah, it would be.
Oh no.
No, it would be.
Because you wouldn't get -2, and this is not the final answer. This is not X value, but this is rather
Yeah, you plug it into here,
these. You plug it in here,
and then whenever you take it out,
and you gotta remember that
you set these equal
here
to.
you have X plus some value and X plus another value. But we called it X plus X1. And X plus X2.
And then whenever you plug those numbers in, you set this equation equal to 0, so you would get 3. This was
Mhm.
-1 because when you set it equal to 0, bring it to the left, the 1 comes opposite sign. Get this answer right here. And then can you just plot these points on the graph?
No need to do it right now. Before plotting anything, I can give you some room here. If you want to plot it, but it wouldn't give you a lot. You're just gonna waste time on plotting those points without knowing what to do with them later, right?
Mhm.
So let's stop with first derivative once we found these critical points, and let's examine second derivative.
Okay.
So can you differentiate this for me? First derivative?
You'd bring the 2 over, so you'd get 6 x. Subtract 6 because, and then that's a constant, so that's just equal to 0. So you get that.
Okay, and now we need to say it's equal to 0 again, right? Now we say second derivative equals 0 and find evaluators for those values. And we have only 2 possible values when,
You could factor out
oh
a
no,
6.
only one actually possible value when the second derivative equals 0.
You factor out a 6 and you get 6 times x, subtract 1, and then that becomes a 1 when you set it equal to 0.
Yes, absolutely right. So now let's determine the sign of second derivative in the intervals determined by x equals 1. And we're gonna have basically three intervals. Oh no, 2 intervals and 1 point, right?
Mhm.
Intervals before 1 and after. So let's see how this function, what sign this function has when x less than 1.
Okay, so we could do -2.
Yeah,
Subtract, it's negative.
absolutely right. So it would be concave down if second derivative has negative sign, right?
Yeah,
And
Yeah.
to the right hand side from x equals 1, we're gonna have positive values.
yeah.
So concave up. And if we had concave down and concave up, concave down before the point, concave up after the point, we can make a statement now. This is an inflection point.
Okay.
Perfect. And let me clear this. So now applying both of our knowledges, but first derivative test gave us critical points, right?
First derivatives. Yeah, they gave it there. Yeah.
So, and here they are. Here are these two critical points, -1 and 3, right?
Yeah.
Both of them local
Minima.
extrema. One of them is local maxima and the other one is local minima.
Mhm.
And we also have inflection point right here. So applying the second derivative test at x equals 3, we obtain the local minimum point. And how would we apply second derivative at x equals 3? I would substitute x for 3 in this point.
Okay.
And if sign of my second derivative is positive and x equals 3 is critical point, thus it's local minimum. If sign of my derivative in this point is negative, as it is in point x equals -1, right? X equals -1, my second derivative would be negative, right?
Yeah.
So, and x equals -1 is also my critical point, right?
It's -1. Yeah, it's a critical point.
And second derivative negative, so this is local maxima.
Okay.
So we know local maxima, local minima, and inflection point, right?
Yeah.
Knowing that, we can plot this graph basically effortlessly because you literally know everything about it. You know that if this is local maxima and we don't have any other critical points before, it means that the curve was constantly growing up to this point. So we just go ahead and draw a line to this point, like curved line like this, because we eventually stopped, right? Because it's local maxima, and turn the other way around. And here you can see that slope of a tangent line is decreasing because the sign of the derivative of second derivative to the left from x equals 1. Look here, to the left from x equals 1, what happens? I have concave down. Guys,
Mhm.
is it right? To the left from x equals 1, which is inflection point, I have concave down.
Yeah.
Yeah.
My tangent line is above the curve.
Yeah.
And now I have inflection point. Now my tangent line would be below the curve. And it means I have concave up. After I know that I'm going like concave up here. And I know I have another local extrema. It's local. This is minimum. I know that once I reach this point, I basically getting bounced to the other direction from it. So I keep growing and I still concave up here, right?
Yes.
So now you can look at it this way.
Okay.
It's concave up here. Still, sorry, concave down because we're above the curve. Concave down here. Inflection point, and now concave up. You see this?
Hmm.
Yeah.
And that's exactly what we found with second derivative test. Concave down to the left from x equals 1, and concave up to the right from this point.
How did you find the critical points again? I forgot.
So critical points, first thing first, we do a first derivative test. And to find those critical points, we say that derivative equals 0 or undefined.
Okay.
And second, so we found the first set of points, and now we need to find the points of inflection. And to find points of inflection, you need to set second derivative equals 0 or undefined. Make sense?
Yeah.
Any more questions, guys?
That's everything.
So how do you feel? Did you understand this topic today?
Yeah,
Yeah.
good.
It's really fascinating one, and it's really useful one. We used it a lot in further studies after this course at school, and I strongly suggest you to look through it once again on your own to clarify the information that you received from me today, and to make it easier for you to navigate in your home assignment. Okay, guys?
Okay.
Okay.
Oh, thank you for participating. You have a great day. Nice meeting you.
Thank you.
Thank you and bye bye.
Bye. Have a good day.
You
Thank you.
too. You too. Bye bye.